Physics 1A for May 13th. Last time we were looking at this problem, example 5, and we're going to look at solving it today. So we have this mass, it hits this rod, and we had a few things that we needed to calculate here. I think we kind of already solved part A, but we'll go through it really quickly again in case people maybe weren't here or something. So we take our rod, let's use something like this, draw a rod. So there's our rod, and there's a ball that's traveling near it, down here. And it eventually, we'll just draw it, since this is the initial state over here, we'll just draw this as being kind of the final state. So we've got, I don't really want you to shape on. So we've got our ball, it sticks to here. The mass of this object is 2m, and the mass of this one is m. And we know that the total length here, let's give it a name, let's call it L, is equal to 1.2 meters. So this is L, the full length of the rod. The first thing we want to do is to find the center of mass of the combination. I think what we did last time was, for a lot of people, we just said, let's call this point right here y equal to 0. And if we do that, we can define the y center of mass for our system as being equal to this little mass times its coordinate, which is 0, plus 2m. And then we need to multiply that by the coordinate of the center of mass of just the rod, which would be the center of it, which would be L over 2 in this case. So that's, 1.2 meters divided by 2. You divide all of that by the total mass, which is 3m. And I think here we got, what was it, 0.4? Yeah. And that tells us that we know where the center of mass of this object is. And let's see, 0.6 would be there, so 0.4 is like a third of the way down, so something like right here. That right there is we call it the y-coordinate of the center of mass for the whole system, basically. Okay. Now, after this ball hits the object, because it was moving with initial speed v0, we know that the system is going to rotate with some angular speed now, but we also know that it's going to translate, and what's going to happen is it's going to rotate about the center of mass of the system, and then it's going to have a translational velocity that we're going to call the velocity of the center of mass, which goes this way. And I think we calculated this last time. It's pretty easy to use momentum conservation, because this is a system where we have no pivot. Just to remind you about how we handled these, to remember where this came from, or like where you can find the notes for this, because your book does a horrible job of outlining these. There's two situations when you have collisions occur. You either have no friction and no pivot, or you have a pivot. We're in this scenario right here. It says with no pivot, choose the center of mass of the system for an axis, and use conservation of linear and angular momentum. So we do that here to say that the initial momentum in our system was coming from just this ball right here moving. So that's going to be m times v0. And then the final momentum comes from the fact that the two objects stick together. So the total mass is m plus 2m, and we multiply by the velocity of the center of mass. This is what we're trying to solve for. So if we solve that for VCM, we're going to get VCM is equal to, what? Is it v over 3? Yeah, v0 over 3. You guys have any questions so far about that? I think we did all of this last time, or you guys, I think you did it yourself last time, honestly. We didn't completely solve this problem, right? We didn't do this part, did we? I don't even think we actually solved the first part. I think some of you guys calculated it, and maybe you got like something like 0.48 or something like that. I can't remember. Okay. So we found the center of mass. The next thing we want to do is to find the final rotational inertia about the center of mass. So that means to find so this is part A. Part B. We want to find the moment of inertia about this point right here, and I'm just going to call that point P. And we said that you find this by doing moment of inertia of the rod plus the moment of inertia of the ball. And that to find the moment of inertia of the rod, we had to take the moment of inertia of the rod about its own center of mass plus the mass of the rod, which is 2m, using the parallel axis theorem, times d, which is going to be this distance right here. I'm going to call that d. The distance from the old center of mass of the rod to the center of mass of the system is what d represents. So we'll do d squared. I think it's equal to 0.2 in this case, so we can label that over here, that d is equal to 0.2. So we can plug it in later. And then, okay, and then plus moment of inertia of the ball. The moment of inertia of the ball is going to be based on this distance here. Okay, which is, I'm just going to, I don't want to create a new variable. So we'll just say it's the mass of the ball multiplied by the distance from the new center of mass to where the ball is located. And in that case, this is going to be 0.4 meters. And we need to square that. plugging everything in. The moment of inertia of a rod about its center of mass is 1 over 12, the mass of the rod, which is 2m, times the length of the rod squared. Then plus all this stuff, 2m d squared plus m. 0.4 squared is going to be 0.016. And then if we plug in all the numbers now, we should get an answer. So 1 over 12. It's going to be in terms of m, right? So here, we'll do it like this. There's an m times. 2 over 12 is going to be 1 over 6. L squared, L is equal to 1.2. Plus 2, d squared, d is equal to 0.2. Let me know if you guys notice that I'm making a mistake or anything like that. And then plus 0.16 meters squared. There we go. And then we get the moment of inertia about point P for our system. I can't do this in my head. What do you guys get out of this? You said it was like 0.48, is that right? And then I'll say it's meters squared by putting it up there. Is that right? I can't see you guys if you're typing. 1 second. Does that look right to you guys? Okay. This unit's really weird because it's like a mass multiplied by meters squared, but this is just the unit up here. It's just the unit. And this is the letter M. We can do something really simple here too, right? Like, what if we just did this? Let's let M equal to 1 kilogram. How about that? Then this would actually end up being 0.48. And then kg times meters squared. That looks a lot better, doesn't it? Let's do that. Then we can get numbers. I did a very similar problem to it last week. Right, yeah, that one. Oh, thanks for linking that, Jose. Okay, so that's the rotational inertia. Okay, and does anyone have any questions about that part? We're going through this pretty quick here, but since we looked at it yesterday, I hope you guys are prepared to go a little fast. How do I find the final angular velocity? What should I do? What kind of equation can I use? No, we already used linear moment. Oh, did you say angular? That's okay. Yeah, so we're going to say the initial angular momentum is equal to the final angular momentum. The initial angular momentum is going to be, so you do m times v naught, and now I got to multiply by a distance, right? Because angular momentum always has a mass, a velocity, and it's got a distance. What distance am I going to use for the angular momentum initially? Should I use the distance down to the center of mass right here? Should I use this distance down to the new center of mass? What should I do? Which one of those should I use? This one or this one? The new center of mass, that's right. And we can go back here to see why that's the case. You choose the center of mass of the system for an axis. Now that's a little bit vague, but what that means is that you're going to use the center of mass after the collision, okay? You have to use the center of mass after the collision as your axis, because you have to be consistent between part A and part B. Sorry, between like initial and final in terms of what you mean by your axis, basically. You can't change axes, as far as I know. Okay, so the initial is going to be mv naught times this distance here, which I believe was 0.4, right? It turns out to be the exact same distance that showed up right here when we found the moment of inertia of the ball. The final angular momentum is going to be the moment of inertia about point P multiplied by omega. This is what we're solving for now, is omega. That's the angular speed of the system. So now we just have m v naught 0.4 equal to 0.48 times omega. And this is where if we make m equal to 1, we'd have v naught times 0.4 divided by 0.48. And basically what I'm doing here to make this more clear is I'm going to replace m with 1 kg, and then that kilogram can cancel out with this one here. Right? So we end up getting V naught times this divided by 0.48. There's still going to be a meter squared here. And yeah, whatever that is. 0.4 over 0.48 would be like 4 times 10, 4 times 12, 10 over 12, 5 over 6. Is that look right? Yeah, no? Does that look right to you guys? Okay. You don't have any questions? Okay. So we're going to do another problem that's slightly similar, except it doesn't involve an object actually sticking. So it provides for a little bit different type of angular momentum problem. We're going to do this one, and then I have one more to do after that that's related to angular impulse. Okay, so go ahead and read this problem. I'll give you a chance to read it. Take a minute or so. Okay, let's talk about this problem. So 0.2 kilogram ball traveling at 5 meters per second in the direction perpendicular to the plane of an open door. So I'm going to draw this like it's a door, right? So I'm still going to draw it kind of similar to what we did in the last problem. Where's the shape thing? Okay. So we want to imagine that we're looking at the door from the top down. Okay, so this would be top-down view. And there's going to be a pivot point right here. This is like where the hinges on the door are. So this is our fixed pivot. A 0.2 kilogram ball traveling at 5 meters per second in a direction perpendicular to the open door. So we're going to have... it's perpendicular to the plane, right? Okay, yeah, this is correct. So it comes in a straight line, like this. Let's say its initial speed is v naught and call the mass m, and label those variables. So m is equal to 0.2, and v initial is equal to 5 meters per second. The ball strikes a nail in the door, 0.4 meters from the hinges, and bounces off at 3 meters per second at an angle of 30 degrees. Now we have to look ahead here for a second, because the door has a mass of 12 kilograms and a width, and the width is going to be up and down here of 1 meter. So actually I'm going to have to move where my ball is there, but that's easy to do with this application. So this length right here, we'll call it L. It's called width. We're just going to use L for it. I don't like the W symbol because it looks like omega. The length is 1 meter. 1.0 meters. And then the place where the ball strikes the nail is 0.4 meters from the hinges. Okay, so in reality, the place where this ball is should be like 0.4. So if this is halfway up, 0.4 from the hinge would be up here, right? Does that look right? So then this distance here, here we go. That distance there, I mean, do we want to give that a name too? Call it D maybe? The distance D is equal to 0.4 meters. Now, when the ball hits, there's going to be a nail sticking in the door, like right here, basically. That's the best way to put this. It's like there's a nail like this, maybe, in the door. So when that ball hits, it says that it bounces off at 3 meters per second at an angle of 30 degrees with the plane of the door. Okay, so when the ball bounces off, it says 30 degrees with the plane. So the plane of the door would be like this, right? This is going to be what we call kind of the... We'll call this like, I don't know. No. Oh, ink to shape is still on, isn't it? Okay, whatever. Maybe we just call that velocity v and say that v is equal to 3 meters per second. And let's give this angle here phi. And we'll call that 30 degrees. A lot of variables in this problem. I think I got everything now, though. Oh, and then the mass of the door. So let's call the mass of the door big M, and we'll call it 12 kilograms. Okay, so the mass of the door is M. And this is the before and the after. Now, of course, because this mass hits the door is going to swing up like this, right? With some angular speed about that pivot right there, right? And those are the two things we need to figure out. Eventually, we're finding, this is ultimately what we're going to be calculating, is what the angular speed of the door is after the collision. And find the angular momentum of the ball about the hinges before and after the collision. Those are the three things we want to do. Does the problem make sense to you guys? Is the picture clear enough? And do you think the picture is accurate based on what it says in the problem? I think that, imagine that the door was closed, the ball would just bounce off, and the door wouldn't do anything, right? Like, so imagine if it was locked here, right? So that, just, I mean, yeah, the difference between throwing a ball at a locked door versus throwing the ball at an open door. The open door can swing. I think that's the difference, right? Sorry, was that clear enough? Okay. Okay. Sure, okay, so let's imagine we've got a door right here, right? And let's say this is the knob, right? God, I hate it when that just kind of freaks me out whenever you get these shapes that appear, but whatever. So we've got our door, maybe some windows in the door. This would be the plane of the door, right? If you're facing it, right? So our ball is kind of coming in. Imagine the ball, you throw it at the door, so that it impacts like right there, basically, right? The hinge is over here, and the ball is basically hitting somewhere like this. So it comes in from the screen into the screen and then bounces off back like that, right? The ball. See what I mean? And you take that whole thing, you flip it up, so you're looking at top down. That's a good question, because I'm sure that people were confused just like specifically. So we're looking at it this way, right? That's where our eyeballs are looking. And so what we see is the ball comes in perpendicular to the plane and then bounces off at an angle like that. Okay? No problem. So let's do the rest of the stuff. All right, so now the first thing to do is to find the angular momentum of the ball about the hinges. Since it says about the hinges, that means that we're going to be using this point, the pivot, as our point. So let's say we want to find, that's not an L, so let's do this. The first thing we want to do is to find the initial angular momentum of just the ball alone. Stop this ink to shape stuff. What must I do? Does that work? Unclick it? Does that work? Okay. So the initial angular momentum of the ball is going to be, well, this one's pretty easy, right? It's the mass of the ball times its velocity. We need a distance. The distance is going to be d. That's the distance of the perpendicular distance from the ball to where the hinge is. That's d. The final moment of inertia of the ball, that is to say, when this is the final state right here, when it kind of moves off like this, is going to be, I feel like every problem we've done so far, except for the very first one, the angle between the velocity and then the distance was always a right angle. This is an example where it's not. It's the main reason we're doing this problem. So you take the mass of the ball times its velocity. You need to multiply by the same distance d. We're looking at basically the starting point for this velocity vector. And now you also have to multiply by the angle between basically this vector here and this vector here, between the position vector. You could call this vector d if you wanted to, or something like that. You need the angle between d and v, which in this case is going to be phi, or, yeah, it's phi. So you need to multiply by the sine of the angle phi. Okay. That gives you basically, if you think about it, this is how this works. It effectively gives you this component of the velocity, right? That's what the v sine phi represents. Because the other component of the velocity is coming from the fact that there was a nail there, and that nail exerted a force, and that force basically made it so the ball that came in from the left is now going to have a component that also goes down and to the left. So it's going right, and now it's going left, but it's also moving downwards. And that force that produced that downward velocity is coming from the door itself. And that force is going to have the effect of pushing into the pivot upwards, which is why it's not going to affect the angular momentum. I don't know if that made any sense. Maybe I over-explained that. But that's the answer to part A. We can obviously calculate these things. We have the numbers. I guess we should. So mv naught d is going to be... Here, there's a little more room. Okay. mv naught d is going to be 0.2 kilograms. The initial was 5. Yep. And d was 0.4. So the answer is going to... Oh, no, that was awful. Sorry. Just do like that. 0.4 meters. This is going to be 0.4 kg meters squared divided by seconds. That's the unit for angular momentum. L final ball is going to be mass of the ball, which is 0.2, times v, the final velocity, 3, times d, which is 0.4, and then times the sine of 30. And let's see, 0.1, 0.3, 0.12. Do both of those look right to you guys? Okay. All right, let's see part B. No, it actually is negative. I was gonna put that in later, but you're absolutely right. We need to define a direction to be positive. So since the door is going to rotate clockwise, let's make this direction positive. So then the ball would be the one that's negative. Oh, sorry, the after would be the one that's negative, right? Negative sign right there. Thank you for noticing that. That's a very good point. Yep. Okay. Part B. If the uniform door starts at rest, we want to find its angular velocity after the collision. Okay. This is going to be where we're going to use the initial angular momentum of the total system. Should be equal to the final angular momentum of the system. In this case, the only initial angular momentum we have is the initial angular momentum of the ball. And for the final angular momentum, we're going to have the final angular momentum of the ball, plus we're also going to have the final angular momentum of the door. The initial angular momentum of the ball we've already calculated up there. The final angular momentum of the ball is right here. And then the final angular momentum of the door, this is going to be basically the moment of inertia of the door multiplied by that omega right there, the angular speed that it's going to have after the collision. And we just need to solve for omega here, right? What's the moment of inertia of the door? Well, it's basically a rod that's rotating about one end. So it's going to be 1/3 times the mass of the door, which we said was capital M, and then times the length squared. It doesn't matter what the height of the door is, so to speak, since it's rotating about this end over here. Kind of similar to the fact that, I mean, in case that's confusing to you a little bit, if you have a thin like disc like this, and you have a long disc, like consider 1/4 or consider a roll of quarters, both of these objects have the exact same moment of inertia. This distance right here, so to speak, doesn't matter at all. This is not important how long it is, as long as it's rolling about an axis like this, or an axis like this, right? Same thing goes here. This is effectively just a rod that has a length L. So that number is going to be 1/3. The big mass is 12 kilograms, and then L is 1.0, right? Yeah. So this is just going to be 12/3, which is what, 4? And then from this equation right here, what we're going to get is, let's see, I add this to the left-hand side, so that's going to be 0.52 divided by I. Is equal to omega. 13.13. There's 52 cards in a deck, and there's 4 suits, of which have 13 cards each. Okay, 0.13 radians per second squared. Just radians per second, my bad. You always have to throw the radians in yourself. That would be the angular speed of the door after the collision. This problem isn't that much different from the other ones, but it does institute the possibility that an object could have an angular momentum after the collision that might be negative, as well as the fact that the two things don't stick together like they did in all the other problems. So, okay. Is that all good to you guys? Do you have any questions? Yeah? Okay. So let's talk a little about angular impulse. So angular impulse comes from the following equation. If I take the net torque acting on a system, okay, net external torque acting on a system, when a net external torque affects a system, it has the effect of changing the angular momentum of the system, right? Let's think about a really simple example. We have a bicycle wheel. It's mounted on a fixed axis. Like this would be like, imagine you take your bike, you turn it upside down, right? And it's fixed in place. It's not going to go anywhere because the bike's like, resting on its handlebars and seat upside down, right? And then you just come along here and you exert a force like this right here, okay? And you do so at a distance away r, okay? You know that there's going to be a torque that's equal to F times r, okay? So you're just basically taking your hand and you're just hitting it on the top, basically. You're applying a force right here. It produces a torque that's equal to F times r, okay? This is an external torque, and it's going to have the effect of making this object speed up, right? If it started with the zero angular speed, it's going to pick up some angular speed as a result of you hitting it, right? Which is to say it's going to gain angular momentum. The fact that you're putting a force on the object gives the object angular momentum. Now, it depends on how long you actually exert the force. So in order to understand what's happening here, what we need to do is we need to multiply the delta t to the left-hand side of this equation and say that it's going to become, I don't want to change colors, the net external torque multiplied by the time interval over which the torque acts should be equal to the change in angular momentum of the system. And I'm just going to write it like this. Really, there should have been a... The change in angular momentum of the system is going to be L final minus L initial. Okay? And this quantity on the left-hand side here, the torque multiplied by the time interval, this is called the angular impulse. Okay? Well, hold on a second. Let me look at my notes. Is that right? Yeah, we have to have a different name for this though. We can't just call it J because in the past we used J. The notes use the symbol J sub theta. And I guess that's okay. I don't really like it particularly. This represents angular impulse. The theta is for an angle. And you can compare this to another equation that we had in the past, which was the impulse momentum relationship. Which says that the impulse J acting on an object is equal to the average force acting on the object multiplied by the time interval over which it acts, and this has the effect of changing the momentum of the system. And really with these, you can pretty safely make these all vectors. So notice they're very similar. This is just J times theta. And if we think about what this represents in our problem right here, so in this problem right here, let's go back to draw. Green. Green. Yep. So in our problem here, the torque, right, is F times R. So if we have an impulse J, you can also say, so how to say this? If you have an impulse J and you multiply by R, right? So if I take J, an impulse J, and I multiply by a distance R, that's going to be the same thing as F average multiplied by R times delta T, which means that it's actually just the torque multiplied by delta T at that point. So if I'm given an impulse J and I want to find angular impulse, right? If you look at this statement and this statement right here, this tells us that if I have an impulse J and I want to find the angular impulse J theta, I just need to multiply by the distance R. This is generally what we're going to do, okay? Is we're not going to have to worry about this intermediary term. We're just going to say the angular impulse J sub theta is equal to just the impulse J multiplied by R, okay? So big J, this is linear impulse. It's the type of thing that's delivered when a rocket takes off or when you hit a baseball with a bat. And then J theta is angular impulse. But we don't really even need to use this expression because we can just do this, basically. We can say J times R is going to be equal to L final minus L initial. This is, whoops. This is in general how we're probably going to solve problems. Okay. All right. I should really take off this piece right here. Now, all this is summarized in this document here, right here. So we've done a bunch of problems with two-body interactions, right? Two-body interactions. We did a bunch of those, okay? The next set of problems we're going to be doing are linear and angular impulse. This involves a single impulse J on an object. And again, we have the distinction between a no pivot, and a system with when you do have a pivot, right? And the rules are that when you have no pivot, the net impulse is equal to the change in linear momentum. This is what we've used in the past, early on when we talked about momentum. And then when you have angular impulse, you use the center of mass of the object and say that the angular impulse is equal to the moment of inertia about the center of mass times this. This is the no pivot situation. We'll do some problems like that. The first thing we're going to do, though, is a problem with a pivot. In this case, the net impulse is the change in linear momentum. And what happens is there's going to be an impulse at the pivot. So the sum of those is going to be the change in linear momentum. And then for angular impulse, we use the pivot. Moment of inertia about the pivot, etc. I don't pretend to think that any of this stuff is super clear. It's one of those things where it's like, I'll just show you how we do it, and I hope that the application helps you to understand what these things mean. Okay. Before we move on, do you guys have any questions? Again, an impulse is what happens when, like, a baseball is coming towards you and you hit it, or someone rolls a dodgeball or a kickball at you and you kick the ball. You deliver a impulse to the ball. There's a bunch of neat problems on this packet about this, but this is probably my favorite. So a uniform rod with a mass m and length L. I hate this L. We're going to change this to, this is going to be curly L here. That's the total length. The mass is m, the length is L, pivoted at point P, so this is our pivot point. It's resting on a horizontal frictionless surface, okay, so we don't need to worry about gravity or anything like that in this problem. An impulse J is delivered here to a point D, there, which is a distance x from the pivot point. We want to find the angular speed about P after the impulse, and then some other things as well. Okay. So this is kind of our initial picture. Now, what is that impulse? It could be someone with a hammer or something like that, right? So someone takes a hammer, right? And they just smack this rod right here. And then they pull the hammer away, okay? They smack the rod, and it's going to rotate, right? That would be an example of what an impulse would be. So that J you can think of as either being a hammer hitting it, or someone coming with their hand and then hitting it from the side or something like that. It's just a little force that is exerted over some time interval. And it delivers that impulse J. So the final situation then is going to be that after this impact occurs, the rod is going to be swinging. It's fixed to pivot at that point right there, so it's going to swing up some. And it's going to be swinging with some angular speed. And that's what we want to calculate now, is what is that angular speed going to be. Okay. So we're going to use the equation that we just stated, which is that the impulse J multiplied by the distance to the point where the impulse is acting from the pivot. This is our pivot at the very top right here, point P. So that distance is x. This is going to be equal to the change in angular momentum of the system. So the final angular momentum minus the initial angular momentum in this system. Because the uniform rod is resting on a frictionless horizontal surface, the initial angular momentum is 0. And the final angular momentum is going to be given by the moment of inertia of this object about point P multiplied by omega. And we can solve this, especially if we state that the moment of inertia about point P, because it's a rod that's hanging from one end or resting from one end and it's rotating like that, is going to be 1/3 multiplied by the mass of the rod, which is capital M, times the length of the rod squared. Plugging that in here, we get 1/3 ml squared multiplied by omega, which we're trying to solve for, is equal to just J times x, impulse times x. And all we can do in solving this then is just to say that our answer is going to be 3 times J times x divided by the mass of the rod times its length squared. That's the angular speed that we're going to get out of this. Now, it's just a bunch of symbols, and I know that doesn't mean much, but this is just the first step in kind of working through this to get something that makes some kind of sense out of this. Does anyone have any questions about that? Okay, part B. Find J prime, the impulse caused by the pivot in terms of L, X, etc. So what does that mean? What that means is that when this force J, or this impulse J, excuse me, when this impulse J hits the rod, there is going to be a force at the pivot, okay? Whoops. And what that force is, we don't know. Maybe it's gonna, I'm having a hard time drawing leftward, so I'll just go like this. maybe there's an impulse at the pivot here, and we call that impulse J prime. J prime represents the impulse at the pivot. And this is where I want you to kind of think about what's going on here in the following sense. Well, let me just ask this question. Does it seem reasonable to you guys that if you hit this this rod that's hanging here, and it has a fixed pivot at this point at the top, that if you hit it, that there's obviously going to be some force absorbed by the pivot? I say obvious, I don't mean that. Is it obvious to you that there will be some force at the pivot? And if it's not super obvious, imagine that this force J was actually hitting right here. Does it become clear that there would have to be even more force at the pivot if the impulse J was closer to the top? And that if you take that to the highest extreme, and we take this force J and we actually apply it directly at the pivot, right? At that point, this impulse would basically not cause the door to move at all. Would you guys agree? Like if you hit the door, or this rod, or whatever this is, right at the pivot point, then the door's not going to rotate, right? And there's definitely going to be a force right there at the pivot. That's the extreme situation, right? Does that clarify that for you guys? Am I over-explaining this? I don't know. So there has to be some kind of force there, right? There has to be some kind of force there. Now, something else I want you to think about while we're going through the rest of this problem is, instead of this being a pivot point right here, suppose that it was your hand, okay? And suppose that this rod was a tennis racket, okay? Or that it was a baseball bat or something like that. And your hand is now the pivot, right? And I want you to think about the following thing. I don't know how many of you guys like played t-ball or baseball or anything like that. How many of you have played tennis or racquetball or any sport in which you have like basically an instrument that you swing with your arm to hit a ball? Anything like that at all. It could be cricket, it could be baseball, tennis, whatever. Have you ever done something like that where you're swinging it and you hit the ball off, like kind of off of what's called the sweet spot, and you feel like a sting on your hand? Does anyone know what I'm talking about? Have you ever played baseball like when it's cold outside and you're holding like an aluminum bat or a wooden bat and you try to swing and hit a baseball? You will feel a sting on your hand if you hit it off the sweet spot. And that sting is this force right here, the force of the pivot. Does that make sense? Do you guys know what I'm talking about? Okay. Yeah, it's just like, and it can sometimes like, it's jarring, right? It'll send like shivers down your forearm and stuff, right? Okay. So that sting you feel is like this impulse at the pivot in this problem, okay? Now, to figure out what it is, we rely on this other equation right here. Since there is a pivot, the net impulse is equal to the change in linear momentum. That equation right there is what we're going to use, okay? The impulse plus the impulse at the pivot is going to be equal to the change in momentum, the linear momentum of the system, okay? So, let's write that equation down. So we take J, instead of playing plus J prime, I'm just going to say minus J prime, because one's forward and one's backwards, and these are vectors, should be equal to the mass of my door multiplied by its initial velocity, or sorry, its final velocity minus its initial velocity. And specifically here, it's going to be the velocity of the center of mass that we're interested in here. That is to say, this velocity vector here. So right after the collision, right, the velocity of the center of mass is what we're interested in. Now here it's kind of moving up a little bit, but you would imagine that it would actually be directly to the right. Right after the collision, at least. Okay, so we know that the initial velocity of the center of mass was 0. To find the final velocity of the center of mass, how would we do that? How would we find the velocity of the center of mass right here? How would we do that? Can we use this? Yeah. Or it's, what is it, VCM is going to be equal to, I would say, the distance to the center of mass multiplied by omega, right? So in this case, the distance to the center of mass is basically what, like L over 2, right? Multiplied by omega. So let's put that in here. You take L over 2, times omega, and that's equal to J minus J prime. Now our goal here was to find j, right? So if we do j minus m times L over 2, now this is going to be equal to j prime. Just adding the j prime. Omega we already have over here, right? So let's plug that in. So we've got 3jx divided by big M and then L squared. Just plugging in omega. And now we can actually pull the j out, and we get this expression that says 1 minus. The masses cancel, one of the L's cancel, and we're left with 3 over 2 j x and then an L. I think that's all that's left over, right? And that's our answer. Now, of course, if we had numbers for these things, we could... Oh, whoops. I already factored the j out. My bad. That guy's not there anymore. Just that, right? Sure. So this is the impulse momentum equation here. Oops. This is the impulse momentum equation here. If there's let me state it this way. Conservation of momentum. What is conservation of momentum? How is that stated? If the net external force acting on a system is 0, right? The total momentum of the system, the linear momentum, is conserved, right? When the net external force is 0, total momentum is conserved. In this case, there is an external force, right? It's this impulse. An impulse is created by a force acting over a time, right? So because there's an external force, it's going to change the momentum of the system. Does that make sense? So that's what this statement says. It says you add up all the external forces, and even the force at the pivot is external if you think about it, because the rod is basically it's supported at the pivot, but the pivot is like fixed to a table or something like that, right? This told us it's like resting on a horizontal surface. So this pivot is fixed in place. It's not free to rotate like the rod is. So effectively, that force of the pivot, J prime, it's going to change the momentum of this object. And the difference between those two is what, yeah. So I think you already understood, but I was explaining a little bit more in case other people. Right. Is that cool? All right. So let's kind of bring this home. So this is all about finding something called center of percussion, and the last part is where we do that. Find the distance x such that j prime is 0. Now this is very easy to do now that we've already done the rest of the problem, and it's all in simples. Find the distance x, right, x, such that j prime is 0. Well, if we want to make j prime 0, all we have to do is just equate this to 0, right? So we say 1 minus 3x divided by 2l is equal to 0, and we end up getting x is equal to 2 over 3 times l. This is the distance from the pivot point to the center of percussion, which is also known as the sweet spot. In sports, they just call it the sweet spot, because it's a lot easier for people to understand that than center of percussion. At this point, if you were to swing the bat or the tennis ball about this point, where this is your hand, right, you would feel 0 impulse. You would not. This is where j prime is equal to 0, which means you don't feel a sting at your hand. Notice also, no, that's all I want to say about it. And as a result, all of the external impulse, right, if j prime is 0 right here, right, all of that external impulse goes into the change in momentum of the system, right? And none of it gets absorbed by the pivot, which means you're going to get the maximum, if you think about the maximum change in velocity of your object, basically, right? You're going to get the most momentum going into the ball that you're hitting, or the whatever, basically, if that makes any sense. Like now what you do is you replace the impulse with the ball, right? So you've got your tennis racket. Okay, here's your tennis racket, and it's like kind of coming out of the page that you guys. There's your tennis racket. Okay, this is the pivot point P, where you're holding it with your hand, right? And instead of having an impulse now, let's just replace it with a ball. So a ball comes in, right? And you want to basically take this ball and you want to return it back to the other direction, right? And you want to do so in such a way that you get the maximum, like let's say you just want to hit it as hard as you possibly can, right? The best thing to do is to make sure you hit it at a point that is something like this. Now, what that distance would be is dependent upon the moment of inertia of the object, right? But in this case, it was 2/3, okay, for a rod. If it's a tennis racket, it's going to be something different. It's going to be related to this quantity right here. That's everything about what our answer is came from that quantity. The 1/3 came about because of the moment of inertia, right? So the sweet spot is dependent on moment of inertia, basically. If the object is weighted more heavily down at the bottom, the sweet spot might be farther toward the bottom. If it's weighted more heavily at the top, near the pivot, the sweet spot may be closer to the pivot. It's going to be all about where the weight distribution is, or the mass distribution. It's not about weight. Anyway, I think that's a pretty cool problem that kind of describes the idea of what a sweet spot is. And of course, we have demos for this at school, but I'm sure you can kind of picture what's going on here, I hope. Okay, that took a little less time than I thought it would, actually. Does anyone have any questions? Yeah. You don't need to apologize. Yeah. Yeah, exactly. You're summing up all of the impulses, right? You know, just as an example, imagine that there was an impulse that pushed to the left, and at the same time an equal impulse came from the right. The change in momentum would be 0, right? Right, if I take this rod and I hit the left-hand side with the hammer and you hit the right-hand side with the hammer and we hit it exactly at the same time, the object's not going to go anywhere, right? So you do have to sum up the total momentum, or yeah, the total impulse, basically. And that includes this impulse up here, which it may not be obvious that there's an impulse at the pivot, but I think if you think about it, right, the closer that you get to the top right here, the bigger the impulse becomes. So yeah, in fact, if you let x equal to 0, right, I'm over-explaining now. I think I've answered what you said though, right? Cool. Well, I noticed before class. Okay, we're gonna stop right here and we're gonna answer some homework questions.